Welcome to another video explaining the universe using the particle model. Well, today's video is titled Circular Polarized Light. I've been going over some words that we use in physics and cosmology, and these in red I've covered: speed of light, c, forces. Linear polarized light is what I covered last time. We'll look at that a little bit here, but today it's about circular polarized light. And somebody has asked me a question about an antenna, which I hope to get to once I get through this. Well, the viewer asked originally, does the particle model have a way of explaining the electromagnetic wave polarization? And that's partially what I covered last time. Here is unpolarized light. And there's three different waves here. Actually, there's many different waves. But in particular, there's a horizontal green one, a vertical red one, and another one at an angle. And when it goes through a vertical polarizer, you only get the one. And this is unpolarized. This is polarized. And this is really a complex drawing video of a what circular polarized light is. We'll get into that a little bit. Now, originally, and I covered this last time, the electromagnetic wave is generated by a charged particle oscillating about an equilibrium position, and is an accelerating charged particle. It's accelerating. It moves up, stops, accelerates, and moves down and stops. So it's accelerating, moving up and down, and as it does, the electric and magnetic field that surrounds this charged particle causes the field to vary like this. This is what they say. And this is magnetic, electric, and the horizontal one is magnetic. Question that was raised by another viewer was what about this oscillating ion? And to me, it's gravity that's making that oscillate, and that's a simple answer, but it takes a little bit more to go into that. So what is a circular polarized light? Well, it starts here with two electric waves. Now they're ignoring the magnetic wave, and circular polarized light consists of two electromagnetic waves perpendicular to each other. One's horizontal, one's vertical, and a 90-degree difference in the phase. There's a phase shift right here, 90 degrees. This one starts first. Horizontal starts first, 90 degrees later. The vertical one is at that same point. And it's the combination of the field, the electric field, right, shown right here, that shows this is the electric field of the horizontal, but the vertical is zero, so it's just a horizontal. Over here, the horizontal is zero, and it's just a vertical, and in between is a combination of the two, and it's this strange thing that looks like it goes around in a circle as the wave propagates. That's why they call it circular, because the electric fields, the combined electric fields of two electromagnetic plane waves combine to make this circular pattern. Well, the last time I showed that the particle model, we don't have the same kind of light at all. We don't even have an electromagnetic wave. What we have are streams of particles with a repetitive pattern. And this picture is one of these streams coming out at you vertically, or towards you. And even though that shows one particle, behind it is a whole stream of particles that are coming at you. Now, when this unlayered or non-polarized light hits a vertical polarizer, then some of they get blocked, but the ones in between come through, and that's vertically polarized light. And you have a very similar pattern, only it's horizontally polarized. This is vertically layered. This is horizontally layered. It's easier to say layered because it really is describing what's happening, how some of the vertical ones get blocked in the horizontal, and you have a layered structure of light. That's what we talked about last time. But what's the big deal about polarized? Well, one of the things that's really good about the polarized light is that when you tilt it, this is tilted a little bit down on the right, but you can see through it. Whatever light is going to be there comes through. But you tilt it up on the right, and it's blocked. This is linear polarized light, not circular. With linear, you tilt your head and it gets blocked. I apologize for the confusion. So that's a problem. If you're sitting there watching a movie, 3D movie, and you tilt your head enough, you don't get a very clear picture. But with circular polarized glasses, you can actually lay down and watch, because whether you tilt it down here on the right or tilt it up on the left, you still can see through. It's not blocked. That's the advantage of circular polarized light. And when the question is, well, how in the world does that work? Well, the circular polarized light is made from calcite crystals, this is a natural type crystal. There are manufactured versions, but what these crystals do is, as you can see, when you lay this crystal on a piece of paper that has a line and one word, you actually get two images. And this picture over here shows in general what's going on. The calcite crystal is actually a rhombus-shaped crystal. The crystal atom itself, it's a complex atom that is a rhombus shape, 109 degrees here, 71 degrees here, and when the light comes in straight, it goes through straight. That's kind of what you see here at the bottom line, comes through straight. But there's a 6.2 degree deflection here that creates the other image. And this is a little bit confusing. This 6.2 degrees does not match these numbers. If you use these numbers to calculate the angle, you'll find that this looks parallel to this line, and I don't think it's drawn accurately enough, because I get 19 degrees. I get 19 degrees for that angle when I use these numbers, but they're saying, no, it's only 6.2. If that's true, then this is a refraction, which is interesting because refraction usually only happens when you come in at an angle. This is coming in straight. The ordinary ray goes straight. The refracted ray goes 6.2 degrees. Must be refracted because it goes straight again. And that is a feature of this crystal. So this is an important part of explaining how these 3D glasses work. Here's a crystal. Well, there's a lot of, there's 8 different, what looks like 8 different crystals sitting here, but it's not. When you go from the calcium atom to the calcium atom, here calcium atom, this is the size of the crystal. It takes 8 of these little sections to put it together. but in this form, it's got calcium, and it has a carbonate, CO3 molecule, actually, and then that's shown again here. You have the black dot. The black dot is the carbon, and the three orange dots are the oxygen, and then there is the calcium. A very complex structure, but again, it gives you the same problem. And is this a refraction, or is it just another path it's following? It appears like it's refraction. So here's their three circular polarized light, which I just went through with two electromagnetic waves at right angles and 90-degree phase shift. Question is, with that, how do you get the 90-degree phase shift? Well, if you take this crystal, I know I drew this as a square, it's supposed to be a rhombus, but if you take a crystal in the direction I showed earlier, this path is longer. So you take one stream of TPM light, I'm talking about the particle model here, and come in perpendicular to the surface. Some goes straight through. This is a short path, it gets there sooner. This is a long path, it gets out later. So there's a phase shift. If you make the thickness of this crystal to be a multiple of a wavelength, and this means it's very often very thin, very thin. This is not drawn like it's actually used in the glasses. It's not that thick. But you make it thick enough to get a 90-degree phase shift. So what I've done here, this is from the projector side. This is the left image that you're supposed to see. This is the right image you're supposed to see. This is the A side of the crystal, and this is the B. Same thing here, except the left is flipped from the right, or the right is flipped from the left. The long path is up, and here the long path is down. And so you get this phase shift, but it's opposite. The left is opposite to the right. Okay, so then this is the whole thing. Now I've drawn this a little bit. Normally, the projector hits the screen, and then the light goes back to you sitting over here. Well, that made things complicated, so I flipped the viewer to the other side, and I put the left eye, the left image here, and your left eye is over here. Right image is on this side, and so it's flipped, but this part of the picture is the same thing. This top, this actually splits into, this one stream splits into two, this one stream splits into two. When it hits the screen, it scatters to all over the place, and scatters to everyone in the audience. And so you're going to get all four images on your right eye and all four images on your left eye. And I've drawn this very specifically to be lined up properly so you can understand it. What this side, in your glasses, you come into the B side and it exits the A side. It's flipped horizontally. Not only that, the right has the long on the upper side, whereas down on the projector, the right, it's on the lower side. So not only is it flipped horizontally, it's flipped vertically. That I'm talking about from here to here, and the same thing happens from here to here. So here's how they get blocked. This is the tricky part. How does it get blocked? So you generate this one. It goes through the long path, and I follow it here. It goes to the long path. It's even delayed more. It's delayed more. And this one, it goes to the shorter path, and then it goes through the shorter path again, and it is moving faster, if you will. This is delayed more. Now, instead of a 90-degree phase shift, which happens here, this blocked one has 180. When you're 180 out of phase, your eye can't see it. But now the right-hand side, there's a single image, generates two images 90 degrees out of phase. This is the short path. It comes first. It comes up here, and if it hits this point, it hits a long path. First a short path, then a long path. The opposite one is a long path. It hits a short path. As a consequence, they each go through one long, one short, and they come out even. They're in phase, and you can see it. That goes to your eye, and you can see it. So you end up with a 90-degree phase, 180-degree phase shift. They call it blocked. It's not really blocked. It really gets to your eye as well, but you can't see it. Now that requires it to be lined up precisely in the way I'm drawing it. I think that's the way it works, but it gets a little bit complicated when you start twisting things. But here's my comment about it not being blocked. Here's a phase 0 TPM light with a peak, a valley, and a peak. Another one that's 180 degrees out of phase, peak, valley, peak. And when these things are out of phase by 180, they combine and give you a continuous stream. All right, I know my drawing isn't continuous, and it's only from here to here that I've got it doubled up. Yeah, this isn't doubled up, and at the very end it's not doubled up, but this is a continuous stream. Your eye looks for changes. A continuous stream will put continuous pressure on your eye, but a stream like this will put a pulsating pressure on your eye at a given frequency and send a proper signal to your eye. So they're not blocked, they're just out of phase, and you can't see it because of the AC part of this. The light is gone. Now, when you tilt them, my picture isn't good enough to tell even me how it works when you tilt those glasses. But what all they do, they don't explain about the phase. They show you these fancy drawings with these are the right-centered polarized light and left, right and left, and when it goes through this one, ones get blocked and this one doesn't. They don't explain it. The only answer I could come up with is the phase and how that quartz crystal could possibly recombine in such a way that if it goes through, it's because they're in phase. They're back in phase, and this one is 180 degrees out of phase. They don't explain that. Yeah, and so if you tilt this, I'd have to be able to draw three-dimensional drawings, be able to draw the crystal to see what's going on, why the image is maintained even when you tilt your glasses, like I would be tilting my head this way or this way. So I can't explain it. This is a partial answer, if you will. Gives a hint that the particle model could explain circular polarized glasses, and in fact explain it in a much simpler way than with rotating electric fields. My name is Bobby Hilster, and I am your particle model guru. If you have a question, ask Particle. Thank you for your attention.